So a really interesting type of problem that we can actually talk about when we're talking about KSP is just deciding whether or not a precipitate is actually going to form. And anytime when you're dealing with an equilibrium system and you want to try and figure out whether or not something is going to be happening, that's essentially a Q calculation. Now, what you probably remember from before is that Q is like a dipstick test. So we don't know whether or not we're at equilibrium. We need to kind of decide not only if we are, but what direction that we would be traveling to get there. And Q is going to use concentrations in the moment, not necessarily guaranteed to be at equilibrium. So instead of reviewing too terribly much with Q, which you can go back and kind of watch the Q video later, why don't we just jump right into a problem here and directly apply it to this solubility product material. So here's our first problem. Will a precipitate form when we mix 100 milliliters of a 0.01 molar potassium sulfate solution and 100 milliliters of a 0.1 molar lead 2 nitrate solution? Now, the first thing that I really think about here is that I'm mixing two solutions, and where equilibrium is concerned, I'm really nervous about knowing the initial molarity when those two solutions are mixed. Because even though the 0.01 molar solution of the potassium sulfate goes in as 0.01 molar, it doesn't stay that way for long. So I just kind of want to envision pouring two solutions into a container, and each of them has a volume of 100 milliliters, but combined they spread out over a total volume of 200 milliliters, and that does affect their initial molarity. So I'm actually going to adjust their initial molarity using the equation M1V1 equals M2V2 for both the potassium sulfate solution and for the lead 2 nitrate solution. So I'm just going to plug and chug some of the numbers that I know. First, starting with the potassium sulfate solution. Potassium sulfate starts off at 100 milliliters of 0.01 molar, and it spreads out over 200 milliliters. And then I'm just going to solve for the final molarity, and that comes out to be 0.005 molar. Let's kind of rinse and repeat and do that for the lead nitrate solution. So plug in the original numbers that you do know, 100 milliliters of a 0.1 molar solution, now spreading out over 200 milliliters, and solve for X, the final molarity. That comes out to be 0.05 molar. Well, that's all well and good, but it still has not really started the problem. So what I do know is going to happen is that when I add together the potassium sulfate and the lead 2 nitrate, that a reaction should occur. And that reaction is going to be a double replacement reaction that should form potassium nitrate and then lead 2 sulfate. Now, I also know that if this question is talking about this precipitate, that is my precipitate, my lead 2 sulfate. Unfortunately, as part of this equation, I featured a single arrow, and that's correct that it should be a single arrow. But single arrow implies stoichiometry, not equilibrium. And if I'm trying to figure out whether or not a precipitate is going to form, and I'm trying to perform a QSP calculation, I need an equilibrium expression and some sort of an equilibrium equation that goes along with that. Now, if I'm trying to form a precipitate, that means I'm going to try and use a solubility type expression for that. So I'm just going to rip my precipitate out of this equation and split it up. So I really want to rewrite the equation to look something more like this. The lead sulfate dissociating into lead 2 plus and SO4 2 minus. This is much better because now I have a double-headed arrow, and that implies equilibrium, and now I have something that I can actually do a Q calculation with. So what I do know is also this. I'm going to need that lead concentration. Now, the lead concentration, luckily, is going to come from the lead 2 nitrate. There's a 1-to-1 molar ratio between lead and lead nitrate, so the concentration of that lead must be 0.05 molar. The other number that I'm going to be interested in is the concentration of the sulfate, and I'm going to get that from right here. Luckily, there's also a 1-to-1 molar ratio between sulfate and potassium sulfate, so the concentration of the sulfate is also 0.0050 molar. Now I can write an equilibrium expression, and I went ahead and I just looked up on a huge table of KSP numbers the KSP for my lead 2 sulfate. And that came up to be 2.53 times 10 to the 8th. So that's going to be the touchstone that I compare my work to. I'm going to write my equilibrium expression out next. So QSP, or it could be KSP, it doesn't really matter, is defined as the concentration of lead times the concentration of sulfate. And again, the PbSO4 is not showing up in this expression because it's a solid and its activity goes in as a 1. So let's start to plug into the numbers that I know. First, the concentration of the lead as 0.05, and next the concentration of the sulfate, which is 0.005. And a little multiplication later, I should have the value for Q. That came out to be 2.5 times 10 to the negative 4th. Now, does Q equal K? No, it does not. So does that imply that we were at equilibrium? No. But now we need to try and figure out whether or not a precipitate is going to occur. Now, I do know that Q is much, much larger than K. Now, when Q is larger than K, which direction do we proceed? Q is product heavy. So Q has to move back toward the reactants in order to kind of alleviate some of that pressure. Now, if you're taking a look at the equilibrium expression, that means that we're going to be moving away from the dissociated form toward the undissociated form, where the PbSO4 solid. I should be able to see precipitation here. Now, there's a little rule of thumb here. Although we mathematically calculate that we should see precipitation, our human eyes do have their limitations. We're a little bit different than, say, like, a machine, which has a lot higher sensitivity to different things. Typically, humans are only able to see precipitation when there is a 10 to the 3rd difference between your Q value and your K value. Now, in this case, Q equals 2.5 times 10 to the negative 4th, and K is to the negative 8th. That's a 10 to the 4th difference. I would actually put my money on the fact that we would, in fact, see a precipitation if I add these two solutions together.